Understanding generalized linear models can help you whether you're a researcher, a student, or anyone using statistics to make sense of the world. I'm going to start off with some really basic information, so I'm including timestamps in the description in case you want to hop around. There are tons of resources on GLMs, but a lot of them assume you already have a foundation that I just didn't have yet when I was starting out with data analysis. When I'd ask professors for help, they'd write equations I didn't understand, and when I would look up statistics terms, I would need definitions for the words used in the definitions. There were so many layers of concepts I didn't get. It felt like an infinite onion of confusion. I think most mathematical and statistical concepts are way easier than they first look, if they're explained properly. The easiest way to use GLMs for real data is using code. I personally use a programming language called R, which has great built-in GLM functions. Although we won't be running the program today, I'll show some basic code and then break down the parts. GLM stands for Generalized Linear Model. A statistical model can describe and predict trends. We use existing data to describe relationships and find trends. The relationships we describe are between two variables. For example, we could test for a correlation between the number of flowers and the number of bees in a meadow. When producing models, we often want to create a line of best fit that accurately predicts values. The generalized part of GLM refers to how flexible this type of analysis is, in that it can be used with lots of data types and distributions. We'll go into more detail on that later in the video. Let's review what a linear regression is. You're likely already familiar with this part of a linear model. Did you learn the equation of a line y equals mx plus b in grade school? If not, no worries. I mostly remember it because I learned it with a Weird Al-style parody of YMCA by the Village People. I'll drop a link to a performance of that masterpiece below. Let's review what the components of the equation mean, and then look at an example. X is the value you're putting into the equation. It's multiplied by the coefficient m, which defines the slope, or to what degree y changes with each incremental increase of x. B is the intercept, which tells us what value y is when x is equal to 0. When we have all that information, we can solve for y. When you apply the equation of the line to real data, it's probably not going to be a perfect fit. That's why models like GLMs need to take error into account. Say you're in a band, and we want to see how much money you make when you go on tour. Using data from past tours, we can produce this line to estimate how much money you'll make based on how many gigs you play. If you play no gigs, you might still make some money from your mom buying your album and a t-shirt, hence the intercept that's above 0. With each new show you play, you'll hopefully make a bit more money on your tour. Of course, the real world isn't smooth and predictable like a straight line. You're probably not going to earn exactly the same amount every night of a tour. We have to collect data and evaluate how well the model suits it. There are a number of ways to do that, so when you make a GLM in a program like R, the program will output statistical test results along with slope-intercept information. This example could be called a linear regression. Regression just means a model that creates an equation and a line to best fit the data. The use of the word regression in statistics can be confusing if you're used to the term referring to deterioration or returning to a past state, like forgetting how to ollie or rejoining Neopets as an adult. But in statistics, it refers to how we can go back and look at the past data to explore the relationship between a dependent and an independent variable. One of the ways to evaluate how well a model fits is by measuring residuals. That is, how much each data point deviates from the predicted value. Residuals can be explored statistically, but it's also helpful to be able to look at a plot and say whether the model makes any sense. This looks appropriate for this data. But if our data looked like this, I would say that our model doesn't make much sense. Even before looking at the statistical output of any tests, we should be skeptical. Just because we can plug data points into a program and spit out a line doesn't mean that there's a statistically significant correlation between variables. On the other hand, if our data looked like this, it seems to me that there might be a different trend going on here. It's possible that your tour could net money as you play more shows up to a point where traveling expenses, vehicle maintenance, and decreasing attendance could make your net profits go down. That's why the flexibility of GLMs is so important. We need to account for different types of data distributions. I'm going to break down some code, then explain how to apply different distributions. This is what basic code looks like when you're creating a GLM using the programming language R. You can use it for free, either in your browser or with a downloadable program called RStudio. I'll include links in the description. Other languages like Python will have a slightly different format, but with the same building blocks. The unhighlighted text is the formula, and the highlighted text is where you'll input your own data and information. This is the call that tells the program what we want it to do. In this case, we want it to create a GLM. It goes without saying that you need to have data before you can analyze it. Your data will be organized into rows and columns. We call this structure a data frame. This is where you enter the name of the data frame that you've put into the program. We have to tell the model what variables we're testing from that data frame. We want to figure out how the variable x affects the variable y. You'll have your own variable names depending on the question you're exploring, like height versus running speed, or age versus daily computer time. As we talked about earlier, not all data is going to be distributed in a straight line. Not all data is even the same type of data. That brings us to the next section. GLMs are great because they account for so many different distributions, but we have to know what family our data is in so we can build the model properly. Today we'll cover some of the major distribution families. This distribution may look familiar if you've taken any Intro to Statistics courses. I was taught to call it normal distribution or the classic bell curve. Fancy statisticians call it Gaussian after a smart German guy. Exam results are a good approximation of this distribution. Some students may get high A's and a few may fail, but most of the class will probably get B's and C's. That's why this curve is at its highest point in the center. Teachers may look at this curve to see whether a test was too difficult. Other variables like birth weight and the height of adults are normally distributed as well, with some values being really high, some values being really low, but most being somewhere in between. Count data is often considered to be in a family called poisson, or poisson as my American professors called it. It's named after a smart French guy. If I counted the number of dogs I saw every time I went to the park, that data could be poisson. I could use this data to figure out when to go to the park to maximize the number of dogs that I see. We could look at a variable like air quality to see if it affects how many dogs get brought to the park. Hey, some people don't check air quality before going outside, but I'm still shell-shocked from California's last fire season. Gamma distribution happens when we have positive variables that are really skewed or unbalanced. For example, wait times are often gamma distributed. If we're waiting for the train, and we know trains are supposed to come by every 20 minutes, there's a strong probability that we'll be on the train in about 20 minutes or less. It's also reasonably possible that we'll be waiting a bit longer, but there's still a small chance that we could wait for an hour or more for a train to come by. I love public transit, but occasionally things go wrong. Since gamma distribution might be unfamiliar and sometimes gets confused with Gaussian/normal distribution, I'll give you one more example. Los Angeles gets about 15 inches of rainfall each year. It's certainly possible that they'll get a bit less or more. There could even, hypothetically, be a bizarre year in which they'd get even more rain than Seattle. But that's really unlikely, hence the major skew, hence the gamma distribution. Here's a mnemonic for avoiding confusing gamma with normal/Gaussian distribution. Normally, people don't turn into the Hulk, but gamma radiation skewed Bruce Banner's DNA. Oh boy. If instead I kept track of something with only two possible results, like whether or not I missed the train, That data distribution would be considered binomial. I could make a model that predicts whether I'm going to catch the right train so I can get to work on time, based on what time I wake up. The shape of that line would look something like this. Here's what the model might look like plotted with data. Sometimes I might get lucky and catch the train even after my model tells me I probably won't. Sometimes I might get unlucky. But this model does seem to be a good approximation of what results I can expect. Another familiar example of something with binomial distribution is the home pregnancy test. People will get positive or negative results as determined by levels of a hormone associated with pregnancy. Occasionally people get false results, but it's overall a very well-fitting model. Here's the final bit of information I think you should understand about making your first GLM. The term link function refers to how the model's output is transformed. That's one of the most important ways a GLM is different from a standard linear model. Link functions help make sure the values predicted by your model make the most sense for your data and the constraints of reality. Here's how. The first thing link functions do is make the model's predicted values fit the data better. This basic y equals mx plus b line looks like a decent fit, and statistical tests might back that up. But this line would be an even better fit, both visually and statistically. That's one of the ways transforming our GLM output can be important. Here's another reason link functions improve models. Let's go back to our example of a poisson model. I might not see any dogs at the park if the air quality is terrible, but there's no way I'm going to see a negative number of dogs. A model that predicted I'll see -5 dogs would be incorrect, no matter how much smog and smoke is in the air. The default link function in a Poisson model is a log. Adding a log function to our Poisson models means that our predictions may approach 0 but never go below it. Different data distributions will have different link functions to make sure our predictions are most appropriate for that type of data distribution and ultimately grounded in reality. Here's a table that shows the default link functions for the distribution families that we went over today. These are the link functions that your GLM will use unless you specify otherwise in the code. I recommend sticking with these for now. There are also more distribution families that we didn't cover and more variations on those we did, like negative Gaussian and quasi-Poisson. As you get more comfortable with this kind of statistical analysis, you can tinker with your model's link function and start exploring more types of distributions. What we've covered today should give you a foundation of this useful and versatile way to explore data. Thanks for watching my first ever YouTube video. Let me know if it helped, and start thinking about how you can use GLMs in answering your own questions about the world.